Welcome back, everyone. We're very happy to have Smitha Vishveshwara from the University of Illinois at Urbana-Champaign, and she'll tell us about probing Anyon correlations in black hole-like and black hole-like dynamics in the quantum bulk.
Thank you so much to all of you organizers for inviting me to this beautiful meeting. It's always a joy to be back at ICTS, and as Rajesh Gopakumar mentioned, in some sense, it's my second act. The first one was a book event at the Bangalore Planetarium. So that was an outreach, and now this one is going to be something that it's a long story that goes back over 2 decades concerning anyons, and you heard beautiful talks this morning on the quantum Hall system and fractional excitations. So I will pick up where that was left off and tell you a little bit about some of the past and how we got to, it's an exciting time with anyons actually being detected in the quantum Hall system. So some of the theory work that we've been doing with sort of renewed verve, I will tell you about that journey. And in particular, I will tell you about bulk anyons, how in a point contact kind of setting, you might look at various properties. And I will also tell you about how this beautiful system with edge states and a very rich bulk can also act as something where you can look at black hole parallels. Is there an echo or it's okay? There's no echo, right? Echo. No, it's okay. Okay, yeah. So just to give you a little roadmap, let me put the whole thing in context, our work. So a little bit about anyons and briefly edge geometry and why we ultimately chose to look at the bulk. Also, what's the experimental motivation as well for some of what we'll talk about here. Once we do that, I will present to you a description of coherent state anyons in the quantum Hall bulk. And we found that there's some beautiful analogies with quantum optics and coherent states in that setting. And so it's actually possible to borrow insights from quantum optics into this realm. And then in particular, one finds that saddle potentials are quite common in the quantum Hall system. They're quite ubiquitous. And in particular, in quantum Hall point contact geometries, you have a very natural saddle potential forming. And what's beautiful is that you can use the underlying structure of coherent states in the lowest Landau level to exactly analytically study some features of coherent state anyons in quadratic potentials. So once we see that, we can look at things like, it turns out that a saddle potential where you have 2 incoming states and 2 outgoing states, that acts as a natural beam splitter, and we'll look at some of the dynamics signatures of anyons in that setting. Finally, I'll tell you that that very same setting acts as a parallel for looking at black hole-like dynamics, and in particular, 2 features of black holes. One is the Hawking effect. So when you look at black hole evaporation and the like, it's a truly quantum process, in some sense, a quantum process related to black holes. And this provides a really beautiful parallel for that. And then finally, another distinguishing feature of black holes is what's called quasi-normal modes or ring down. It's the way, in a sense, if you perturb a black hole, how does it speak to you? It does so through these quasi-normal modes, which were also being observed in LIGO and the like. So that's the roadmap, but obviously, I don't have time to go into all the intricacies, so it'll just be a sweeping view taking you through this journey. And very briefly, these are some of my wonderful collaborators on this project. Varsha and Suraj were my students. Preeti is now my student. Barry is my colleague. And Hans Hansen also a very close friend and colleague in Stockholm University. And some of the foundation, in fact, goes back really far back. Mike Stone and Deeptiman, we had a lot of fun exploring these coherent states. And then we built it a little further with Nigel Cooper with the saddle potential. And then this is my father. He's no more. He's a late black hole physicist. So quasi-normal modes is something that he predicted in black holes in 1970. And the book that we mentioned, it was written as letters between father and daughter, between me and him. So, and so you can see that a lot of the black hole physics that comes in there, it was primarily through the kinds of things that he studied. And then Suraj also ended up being his student, so he could translate between condensed matter and, he's in IISc Trivandrum, so I should have put that thing. He just started his faculty position. Okay, so let's begin. And as I told you, I already gave you the roadmap. So as we heard from Giuseppe Musardo's beautiful talk, the 2-dimension allows for fractional particles that have fractional statistics. And while that talk focused on non-abelian anyons, we will study abelian anyons where under exchange, so these are neither fermions nor bosons, so under exchange, they actually pick up a phase factor like so, where alpha can be fractional. And again, as we saw this morning, the quantum Hall system is a beautiful playground in which these kinds of, now these are not fundamental particles, but these are emergent excitations of the system that can have this kind of fractional statistics. They also have fractional charge. So if you look at Laughlin states, which we already heard about, so that's if you look the quantized Hall conductance goes as nu E squared over H, so a universal combination of universal constants. So nu can be a fraction, and so for Laughlin states, it's going to be 1 over an odd integer. And so if you look at the Laughlin states, fractional charge, it goes as nu times E. So these are the quasi-particle excitations. And then fractional statistics, when you look at the exchange, it turns out that that fractional phase is exactly nu for these states. Okay, so now going back to experiment, what's so beautiful about the quantum Hall system, there's many beautiful things, but it's wonderful the way theory and experiment truly go hand in hand. New geometries, new predictions. In fact, Anindya will tell you some, I think, related experimental things too. He's done a lot of beautiful work on that. So it's a very exciting field where these two can really go hand in hand. So in the late 90s, there was some point contact geometries where it was shown that theoretically it was predicted that if you look at the noise, that can show you signatures of fractional charge. And it was amazing that within maybe 1 or 2 years, the experiments were done and these particles were shown, quasi-particles were shown to have fractional charge. Now, it took quite a long while, a lot of experimental progress and innovations to finally show that they also have fractional statistics. And so there's lots more work that's come out, but during the pandemic, when we needed something to lift our spirits, for those of us in the field, in 2020, this came out, these 2 works in tandem that used very different principles, and they actually showed that, that this was a beam splitter geometry, and then this was an interferometer, and they showed signatures of this fractional charge. So here, do they bunch or anti-bunch? Do they behave like fermions or do they behave like bosons? Here, do they pick up a fractional phase when one particle goes around the other? Okay, so let me just say that, so this is the geometry that I told you about, 2 incoming particles, 2 outgoing particles, and what do they do? So a lot of us, including our wonderful chair here, we've been studying, and Deeptiman and others, sorry if I missed anyone, we've been theoretically studying edge state geometries, and lots of beautiful things can come out, and it has tremendous predictive power. So we, in my collaborators and I, we tried to look at how to make these edges, do this kind of beam splitter thing. And I can tell you it's very hard, because as we heard this morning, the edge itself has some dynamics. It's not gapped. So that tends to cloud signatures of fractional statistics. So we'd come up with these weird geometries where maybe we could look at beam splitters and the like. And I was getting kind of annoyed because we couldn't get clear signatures of fractional statistics. And that's when I said, okay, I just want to study the bulk a little bit more, because first off, this is 2-dimensional. This is a fundamentally 2-dimensional setting. And so let's see how the anyons behave in the quantum Hall bulk. And also, the signatures are not quite clear. So we started looking at coherent state excitations, and this is what I will tell you about very soon. And then in particular, we looked at what happens when you put a saddle potential there. Let me just remark that later there were some beautiful works, for example, by Rozanov, Levkivsky, and Bert Halperin, where they used similar things. They came up with a really nice measure, and the interferometry, the experiment that you saw with the beam splitter is based on their prediction. It's also looking at this saddle potential, but it's looking at edge states. So that's a quick sort of not so quick setup. Now what I shall do is I'll say, let's go into the bulk. Let's design what these Anyon excitations look like, or lowest Landau level excitations look like. And then let's look at what happens when you're in the presence of potentials such as the saddle potential, maybe an elliptical potential, and ask, where do the signatures of anyons come in? And as I told you, hopefully I'll have 5 minutes to tell you where the black hole parallels also come in. Okay, so one beautiful thing about this is that in Duncan Haldane's talk, for example, and the beautiful ideas that were presented there, you saw the entire Laughlin wave function. Now, one really nice thing is that when you're looking at quasi-particle excitations in the lowest Landau level, and these are anyons, there's a lovely description where you can forget about all the other underlying electrons and the like. You're just looking at 2 fluxes at 2 different points. And you can treat each of these as just particles in the lowest Landau level that have fractional charge and have fractional statistics. So what I'm trying to say is that if you're trying to study 2 quasi-particle excitations, you can just look at the physics of 2 particles in a very high magnetic field in the lowest Landau level. So it's wonderful. It's like very basic quantum physics. So except there are some caveats like this boundary condition. And so everything that I'm going to tell you about will be built in this setting. Okay, so as we saw earlier this morning, lowest Landau level, these are 2 technical things that I'll show you, but Duncan told you about the guiding center coordinates. What's interesting about the lowest Landau level is that the guiding center coordinates don't commute, because you've projected from this entire Hilbert space just to the lowest Landau level. The lowest Landau, so it's actually like solving a simple harmonic oscillator for 1 particle. And so if you look at these levels, the lowest energy level is the lowest Landau level, and it's infinitely degenerate. So for example, if you were looking at a symmetric gauge, these states would correspond to different angular momentum states. So what's interesting is that now there's a parallel. This is the quantum optics parallel. For regular particles, let's say photons or whatever it is, electrons, X and P don't commute in 1D. That's just Heisenberg's uncertainty. Here, it turns out that X and Y don't commute. So anything that you do in phase space for just regular quantum particles without any truncation, you can do the same in real space. So X and P translates to X and Y, which is why we were able to really borrow a lot from the coherent state description in quantum optics. In quantum optics, so for example, you look at these, instead of angular momentum states, it would correspond to different number of particles. So now, when you look at the most localized particle that you have, it's a wave packet built out of all these circular orbits that you have here. And the coherent state is exactly the one here. And this is the one that satisfies minimum uncertainty. So this is for a single particle. Let me just very briefly say that if you want to do the same for two particles, then what you do is you go into the center of mass and relative motion. The center of mass you treat exactly like a single particle. The relative motion is where these anionic boundary conditions come in. And for those of you that like sort of detailed math and algebra and the like, there's a really beautiful algebra with these. It turns out that you need to have fractional angular momentum states to satisfy this condition. And so one can, in the relative coordinate, what you have to do is you have to use these fractional angular momentum states, and you can build a whole sort of set of coherent states created out of the fractional angular momentum states. And if any of you are interested, there's a beautiful algebra also. We had to play a lot with it, and we could get exact results by using this. Okay, so now let me just take you on a sweeping tour through all the properties that emerge from this. Yeah.
Angular momentum representations are not finite.
No, they're not. So yeah. So that's good. Exactly like the regular angular momentum state. Unless you were on a sphere or you had a disk or something, yeah, it's infinite. Yeah. So there's a couple of things we can do. For example, bunching. This is again, I was teaching a sort of undergrad quantum class where Griffiths, I think, has this thing of a bunching parameter. It tells you bosons bunch and fermions anti-bunch. So what you can do is you can look at the average separation of these particles. So you have symmetrized and anti-symmetrized wave functions. How close do they bunch compared to classical particles? So that's a bunching parameter. And so if it's negative, that means it's a boson because they're closer together. If it's positive, that means it's a fermion. Now we can ask what anyons do, okay? And it turns out that they have a split nature. So if they're really close compared to the magnetic length, so these are fermions here, always positive. Now for anyons, anything that's, if they're really close, there's a kind of statistical repulsion. And Frank Wilczek will say this is like a fifth force. I just heard a talk from him, which makes a lot of sense, actually. You know, we know that Pauli's exclusion, for example, can exert pressure. So, so when you're really close by, they kind of repel each other. But then when you take them far away, this crosses, becomes negative, they act boson-like. Okay, so now this is one feature that we explored. Now the next thing that we can do is, this is if they're just staying static there. But now, and the system is gapped, so you can't really get this moving. So what are we going to do? So what we can do is we can apply shallow potentials and say, how do we get these things moving? Can we see the anionic properties through the motion in quadratic potentials or in any potentials. So, and then for example, in particular, can we get these moving in such a way that I told you about the beam splitter. You have two things coming, and then depending on whether they go off along the, so you imagine a saddle, you have a horse, so you have this coming down, and then it can either go off on either side of the saddle or on the same side. And so if these are bosons, they will bunch and go off on the same side. If they're fermions, they will go off on the other side. And so that is the principle of even modern day quantum optical beam splitters and the like. So, so now, of course, we have a kind of baby theoretical model here, which does give quite some insight. And so what we can do is we can say, let's look at the simplest case. Let's get these things moving with quadratic potentials. Okay, and in fact, that's what you have in this point contact geometry. So just to go back to, that was, so the two groups were Gwendolle Febvre in Paris. His group worked on this kind of beam splitter geometry, and Michael Manfra and group, they looked at the interferometry. So if we go to the beam splitter geometry, it's really this kind of point contact, and you can have two incoming and two outgoing. So we said, let's just look at the bulk. There is a saddle potential here, and you can see what the equipotential lines look like. And so now really these are two different saddles that you have just shifted by 45 degrees. And so then we can say, okay, what can we do? How do we get these particles moving? What happens if they're in the saddle potential? And this is where we really use the whole quantum optics analogy. And let me just say, I already showed you how to create this coherent state. And it turns out that things like the saddle potential, these potentials, in quantum optics, they do what's called squeezing. And so that's quite well known. For example, if you wanted to get, if you have something like this and you wanted to get minimum uncertainty in one direction, you could squeeze like this, but Heisenberg limits, how much, so you pay for it by having more uncertainty in one direction and confining it in the other. So it turns out that these are typical squeezing operators in quantum optics, and we could borrow from that language to figure out what happens with these kinds of potentials. So just very briefly, we were able to, and for those of you that that want to know the details of the calculation, while I don't have time for it, it was a lot of Baker, Campbell, Hausdorff kind of using that again and again, and we could actually get the dynamics under these kinds of potentials. We also use that algebra that I told you about quite heavily, and so we could get these exact results using this. So, so one of the things, I'm just going to show you very quickly. I have 10 minutes, is that right? 10 minutes? Okay, so yeah. So very briefly, what happens is that they follow equipotential lines and they also get squeezed. And so if I look at it very closely, let's just look at one particle. So what that does is you start off like this, follows an equipotential line, and it gets squeezed. Okay, so that's what happens. And then if you look at the relative motion, for example, it's that very same question. Using what we had, the machinery, the theoretical technology that we had for this, we could ask that question, does it act like a fermion? Does it act like a boson? The answer is, it depends. Remember I showed you the bunching parameter. So the answer, so this is something called the Husini Q function that helps you visualize what these coherent states look like. And so what we're doing is we're initializing two coherent states, and then there's implicitly a saddle potential. So you can see they come and then they go off there. So the answer to, do they behave like fermions or bosons, is both. So fermions will always repel, bosons will always go along the same thing. Here, depending on the initial position, if they have a repulsion already, then they'll act like fermions and go along the different thing. But if your initial position is such that they're more boson-like, then they can go off in opposite limbs. So I will summarize. So just to kind of pause for a second, these are some of the features that we found. And again, just to summarize, coherent state dynamics of anyons in the bulk is very rich. And we were able to see some of the features in this toy model with these quadratic potentials. And of course, the big question is, what happens with the full wave function? What happens in experiments? Can some of these things be measured in experiments? Okay, now in the 10 minutes that I have, let me talk about this analogy with black hole-like dynamics. So what happens is, if you look at this, I told you that classically, they're just going to, well, they're going to keep following equipotential lines. So you start something here, classically, it's just going to keep going down. Quantum mechanically, it can tunnel over to the other side. So let's just look at one particle now. But as long as it's on this side, if you look at this x-axis, as long as you start it off here, it's always going to remain below the x-axis. So in a sense, there's something like a horizon here. And so we said, okay, let's look. Is there something, resembling black holes and the like? Obviously, the answer is yes. Otherwise, I won't be asking this question here with 10 more minutes left, because I want to make the most of it. But the thing is, what was beautiful is that it's not just, oh, yeah, this is like an event horizon. The parallels ended up being truly deep, to the extent that my students said, don't just call it analogy. It's much deeper. So now we call it parallels, because they are, and I'll show you. So first thing is, one of the things to tell you about is that en route to this gravitational parallel, I'm going to tell you that if you look at incoming and outgoing states, they are related by Bogoliubov transforms. There's a very nice paper here in 1987 where a lot of this, Fertig and Halperin, they laid a lot of the formalism out. They didn't point to the black hole analogy, but there's a lot in there that's really beautiful and very rich. The other thing is I told you, so if you have y squared minus x squared, I told you x and y don't commute. So in a sense, y acts like p momentum. And really, what you have is you really have effectively a one-dimensional system where in this case, if you have a minus x squared, you have an inverted harmonic oscillator. I don't have time to go into this, but let me tell you that we learn about the simple harmonic oscillator and we can solve for a lot. In undergrad, we never taught the inverted harmonic oscillator. It's an absolutely beautiful system. We used a lot of its features here, and it underlies everything from quantum chaos to nuclear physics, where you have decay in atomic system, atomic nuclei, all kinds of things. And we used this quite a bit in looking at these parallels. Okay, so what are the things? So let me just, again, breeze through this. And of course, I'm here today and tomorrow for part of tomorrow. So I'm very happy to tell you more about this. So you find that there are a couple of features. One is, you saw that there was a Bogoliubov transform. In the gravitational parallel, there's a very close parallel with Lorentz boosts, which are also Bogoliubov transforms. So looking at the same system from two different observers, two different frames, they're related by Bogoliubov transforms. That will prove to be very closely related in the next slide. The other thing is there are two features about this inverted harmonic oscillator. They're the scattering states. Those are related by Bogoliubov transforms. But they're also, when you look at the scattering matrix, there are these decaying states. And it turns out that those are the ones that are related to quasi-normal modes. So anytime you have some kind of potential maximum and you're asking what's the scattering property, you have the usual incoming, outgoing states, but then you also have this very special state that is decaying. So very briefly, let me just say that it turns out that there's a very close parallel between what you see here, this saddle dynamics, and what's called a Rindler wedge. This is in relativity, where if you look at what happens with different accelerating observers, different accelerations correspond to different equipotential lines in the saddle potential. And then we can also show that when you look at the saddle potential and you look at tunneling across, because of the fact that I just made now with this whole Rindler business, it turns out that there's a very specific analogy between particles going from one side of the saddle to the other in the quantum hall and Hawking radiation, where you have particle pair production. And when you look at sort of a thermal black hole, the surface gravity, there's a one-to-one correspondence between surface gravity and the strength of the saddle potential. And so this is something that we've discussed in the past also with Anindya as to whether this can be measured at all in tunneling conductance and the like. Finally, I told you that the other feature of black hole is this ring down. And I'm just showing you here my father's paper from 1970. It was very euphoric. He tells me the story of when he was Charlie Misner's student, and then there's a whole discovery story there. But this is the signature of the quasi-normal mode. The way you do it is you take a Schwarzschild metric, which is outside a black hole. In the simplest case, no charge, no angular momentum. And you find that outside, there is a potential barrier like this. So if you shoot some incoming wave, you can see how this decay takes place. The only thing is to shake up a black hole and make it do something drastic like that, you have to do something drastic, which is why now when you look at the merger and becomes one black hole, at the end of the signal, you actually do see patterns and signatures of this quasi-normal mode. So what we got super excited by is that something that's in the astrophysical setting and also deeply personal, that can be mimicked in the quantum hall. And this hadn't actually been predicted before. Because I'm running out of time, I won't give you all the particulars, but let's just say that this is an experiment to be done in the quantum hall setting and to discover these quasi-normal modes. I love also just looking at the scales. Here we're looking at a mesoscopic quantum system, and then we're looking at something astronomical. So if you look at the energy scales, I've been told by people like Moti Heiblum, who's an expert on quantum Hall physics, that it should be able to, you can shoot picosecond, I don't know the exact numbers, but you can see the time scales here for quantum Hall. It's on the order of nanosecond. If you look at quasi-normal modes in black hole settings, for me, it's really mind-blowing that something of the order of 1 solar mass has signatures as fast as 1 millisecond. So those are the ballparks. But here we have some predictions, and these are yet to be confirmed. So let me just close by saying I just gave you a very quick view of everything that this very rich system contains and how these gravitational parallels are lurking in our beloved quantum Hall system. There's lots of directions that we're still pursuing. So for example, with experimentalists, can we measure this Hawking type tunneling, quasi-normal modes and things? What about skyrmions? What do the parallels look like? Because gravitational waves, after all, it's related to a rank 2 tensor. And then what about the edge bulk connection? We did this edge separately, the bulk separately. How do we connect the two pictures? And then if any of you are interested, we're looking at gravitation, not only gravitational parallels, but combining condensed matter and astrophysics in all kinds of realms. That's something that I'm collaborating on with our gravitational colleagues. Okay, so I think with that, let me conclude where the countdown has begun. So let me just put up my summary here, and thank you all for your attention. I don't know.
Yeah, Arindam.
Sorry. Yeah. What would be your estimate of the Hawking temperature?
So, okay, let me just make a quick comment here. So in the Hawking case, that's a finite temperature thing. The parallel for the quantum Hall is effectively, let's say, 0 temperature. We don't want 0 temperature. We just want temperature low enough compared to the gap. So in the black hole case, surface gravity determines that temperature and the rate at which you have radiation. Here, there's a one-to-one correspondence between that surface gravity and the strength of the saddle potential. So that G, there's, that equates to U, the strength of the tunneling. And so what's really nice is that that's a tuning knob here. So if you have a point contact geometry, you can pinch it more or less. And so you have a controllable knob. And in some sense, you just have to look at the tunneling conductance as a function of energy. And you should be able to extract something like beta times E, where beta is 1 over the strength of the saddle potential. Very good question. So oh, the number. Okay. The number would be for so the gap is what, milli-electron volt? So it's a significant fraction of that. So let's say like 1,000th of milli-electron volt or something. Not too horrible, right? Okay, we can talk, yeah, because it would be amazing to have that experiment done that measures the black hole parallel.
So this is not about black holes. So if you take the, you basically talked about single particle states.
Yeah.
So can these be used to calculate, do many body calculations, at least at the integer quantum Hall level, and see the physics close to the QPC?
Yeah. So I think one of the first things when Deeptiman and I were collaborating with Mike Stone, what was really beautiful for us is we calculated some of these correlators, and then we found a paper by Laughlin in this Pranj and Gervin book where he takes the full many-body wave function, he integrates out all the electrons, like he puts 2 flux quanta or whatever. He integrates all the electronic degrees of freedom, and he just focuses on those 2 points. And those correlators that he got were identical to what we got just from using this 2-particle picture, for example. And the single particle too, we can look at time evolution, interferometry, and all that. So yeah.
You said that in the bulk anyons, it depends on the boundary conditions, right? Whether
Yes.
boson, doesn't it depend also on the anyon parameter?
Oh, yeah. So it depends on how, absolutely, it depends on how close they are. So in that sense, are they really close by? Are they not so close by? But so this is for, absolutely. So that's the Anyon parameter. Let's ignore 3/5. We just put that in. There isn't such a Laughlin state. But if you look at this, we're just going higher and higher in alpha. So you can see that as you separate them out, where they convert from being fermion-like to boson-like, that really depends on that statistical parameter. Yeah.
Thank you.
What experimental signature, I mean, you would expect in the conductance or in the capacitance some Which physical quantity would you see a ring down in?
Okay. So, there are two things. So if we're looking at the Hawking Unru, that's a little harder. That's in the tunneling conductance. I can immediately tell you if you have energy resolved things, you can do that. With the quasi-normal mode, in a sense, that's more ubiquitous. So what you would do is, if you could have pulsed, pulses of these, they can even be electrons. They don't have to be anyons or anything, but just lowest lambda level physics. And if you took this, it should work for an edge state as well. So just pulse it, have it come towards the quantum Hall point contact, wait for long enough, and our prediction is you should see a decaying mode. And that's something that would be quite new, and this should be in the conductance itself. It's buried in the scattering matrix as an imaginary point, actually. So yeah, so anything that can take a decaying mode, conductance, any other measurement, correlations, and the like. Yeah.
That we should thank the speaker.